Okay, yeah, great. Thank you very much for the introduction. So today I'm going to talk about Patrol, which is the probable defense for some adversarial attack against two-player games. So here we are mainly talk about deep reinforcement learning. So it's that we are using deep reinforcement learning to play these games, and then there are some attacks we want to defend against them. So this is joint work from UC Berkeley and the Northwestern University. First, I want to put together some background, right? So what do we mean by two-player game? What do we mean by optimal policy within a game and how to train the policy, right? So the first thing is, what is a two-player game? Here we mainly talk about what we call Markov game. So it's one type of game. Here's an example. It's a pawn game, which we have these two pedals. One is blue, the other is purple. There are two agents controlled by reinforcement learning algorithms. And these two agents, these two pedals, basically they are trying to play some ping pong game. I'm sure like everyone knows the rule of ping pong game. So there are some like specific features or attributes of this type of game, right? So first thing is like we can say both players are in the same world, which means two players can observe the same state at the same time, right? So it's the environment is open to both players in this game. The second thing is like these two players can take action simultaneously. So we can say like it's kind of like time frame, right? So it's like at time 0, both players observe the current status and then take action together, and then the environment can observe these actions simultaneously and then transit to the next state. So it's like starting from time 0, two players take action simultaneously. Of course, they can be different actions, and then the state transit to the next state, and then the players can observe new states and then take action again, and the game just going on until either party lose the game, right? So that's kind of like a background of this two-player Markov game. And then we know that the goal of both players is try to maximize some reward, right? In this case, it's a pawn game, so basically just maximize the score. And here we call it zero-sum game because the total reward of both players added to 0. It's basically just there's going to be just one owner, right? So it's one player win 1 point, and then the other player is going to lose a point. So that's basic background of this game. And then what's optimal policy, right? So we recall that the goal of both agents is just try to learn some policy, get the agent to take some sequence of actions, and then maximize the reward. So the goal here is just try to find optimal policy. Basically, just nash equipment, we know this term has been there for decades long. So in this case, for this type of game, the optimal policy are the policy where we call it nash equipment. So basically, as I shown here, at a nash equipment point, each player can achieve the highest policy, highest reward when its opponent plays the current policy. Basically means, okay, as one player in this game, as long as my opponent stays the same, okay, stays the same policy, and I'm playing my current policy, I'm going to receive the highest reward. Which means, on the other hand, if one player changes its policy, right, it will receive lower reward. So which also means both players in the game, they are satisfied, right? So they don't want to change their policy, which means, right, so in this case, the game is stable. Okay, everyone is happy, we're at optimal and a stable point, which is good. Then the problem is how to get to this optimal points, right? For simple games, it can be a little bit easier, but here we'll talk about this kind of complicated games, right? So where our observation are high resolutional images, which we need some neural network to process them, and then the action space of agent is kind of huge. The policy can be a little bit complicated, right? So here we'll talk about we want to train the policy for both players with some neural networks. In this case, it can be tricky because we know that neural networks, we don't have all those guarantee for the nice properties, right? Whether you can converge okay, but whether are you reaching the optimal point, even local optimal is a little bit hard for neural network. So previous work, what they typically do is they call it self-play. So basically it says, okay, we randomly initialize the same policy, okay, for the both players, right? So we just initialize one policy, we give it to both players, and then as we start training the policy, we're going to select one party. Okay, in this case, maybe we just select blue players. And then we train this, update the policy of this player by playing it against itself, basically, right? So it's like, since at the beginning of the training, the purple and the blue, they're gonna have the same policy. And then only the blue agent updates its policy by playing against its old version of itself. Right after one iteration, and then the blue agent updates policy, it has better version of itself, and then you can copy the policy to the purple agent again, and then just keep working on this. So that's what we call the self-play, because agent is always training against an older version of itself. Of course, it has problem, right? So there are some existing attack, both from the, as you can see, the citations from machine learning community and also security community. We found that actually we can attack such type of agents actually trained by the self-play policy. Okay, I just listed some assumptions and threat model here for the sake of time. I feel like a demo will works out better, right? In this case, this game is like we call it you shall not pass. It's kind of like American football game, right? So we have two players. One is blue, the other is red. The red one is like the blocker, try to block the blue player from crossing the red line, which is finish line behind the red player, right? So we can imagine we watch some American football game. Basically, a normal policy is just these two players can contact with each other and then try to fight against each other. But with the attack, we can observe something pretty interesting. Is that at the beginning of the game, let me just replay it once more. This red player is actually the attacker. So the attacker just establish some very weird behaviors by just running into the ground. In this case, as a normal person, we know for the blue player, just pass it, right? And one can win. But things are different. Oops. It's like, yeah, the blue player also fall into the ground because observe the weird behavior of this red player. So that's kind of saying is like the adversary was able to find some either holes or either vulnerabilities in the policy of the blue player and then just exploit that, right? So, and then comes to our work. So basically it's just what we can do with this type of things, right? Our goal here is that we really try to do some ambitious. It's like, can we get some lower bound guarantees of a defense player, right? So it's like facing this type of attack. Can we train a defense type of, can we train a robust policy, which is robust against some type of adversarial policy, which I don't know the attack before, right? So because like we can know that in the case earlier, if we observe this attack already happen, we can just retrain our victim policy, which is the blue one, and then try to just bypass the attack. But the thing is like, you can always play this type of game, it's endless. We try that, we call it iterative adversarial training, but it cannot converge. So what we try to do is we really try to find some solution, give us a kind of sort of guarantee, right? It's like, I don't need to say the attack, as long as I train, my policy is here, it's robust. Whatever attack gives me, I can at least establish a certain level of robustness. So that's basically our goal. Our method is just like, we look back into a kind of like 2 decades ago theory, in game theory, call it min-max theory, basically saying like, okay, in this case, it's actually equivalent to just trying to find a nash equivalent point. It's like trying to build a robust policy is similar as trying to find a nash equivalent point, right? And then the problem becomes, okay, how to find this nash equivalent point? We know, of course, self-play is not the right way to go because of, obviously it can be attacked. And then we just look back, we found this minimax theory. What is this theory tell us? Basically just, hey, if you can find a policy where the minimax value is same as the max min value, and then that policy, group of policy is the robust one, it's a nash equivalent point, right? And what is min-max, what is max min? Max min basically saying like, measures an optimal reward a player can receive without knowing its opponent's policy. The minimax value is the lowest kind of reward a player can force its opponent to achieve, right, without knowing the opponent's policy, right? So there are like 2 key points here. The first key point is like, we don't know the opponent's policy, which means whatever attack gives me, we don't need to know that. The second thing is like, under this kind of hard constraint, we're trying to find the best policy for each players, right? So, and then it comes to our technique, right? So that, at high level, it's just we're trying to enlarge a huge search space, and within that search space, we're trying to find the point where the min-max is same as the max min. Basically, what we do is like, in this case, we can say, For each party, we initialize a set of policies, right? In this case, 3 policies per party. And then during the training, we're gonna do this iteratively, is that for each party, each policy, we're gonna run it first against all the policies in the other parties. And then try to find the strongest opponent. In this case, the strongest opponent for the player 1, policy 1 is the policy 2 of player 2, right? And then we update this policy 1 of player 1 against its strongest opponent, right? And then in that case, if everyone is playing against a stronger opponent, and then as game goes on, we have a better chance of finding the nash equivalent. And then here comes to some evaluations. So we do this evaluation step by step, right? So first step is that we create some tiny games, which we know the ground truth nash equivalent point. And then we can say, okay, whether our method is better compared to self-play, meaning self-play, and we have some variations of self-play, but meaning self-play, whether our method is better than self-play in finding the nash equivalent point. Right, here are 2 examples that you can see here. So this, this black dashed lines are the true ground truth nash equivalent point. For both games, our method is better than existing method in finding the converging to this ground truth. So that's for the game, we know the ground truth, and we just test, okay, whether our method is better or not. And then we come to some ground truth scenario where we really try to defend against these attacks. So we also choose, in this case, we try to be kind of ambitious. We try different type of games, right? Something from arbitrary games, some from robotic simulation. We even try StarCraft. And this figure basically shows the attack success rate of the attack we know against the agents we train. So basically, this red line is our method. You can see it has the lowest attack success rate, saying that, okay, this method obviously is the most robust one. Here's the result against another attack. Here are some demos. Recall this figure here is we try to use our agent, play against another agent. No, this is the same video I showed you earlier. So this victim agent is vulnerable. And then there's an attacker. And then we replace this victim agent with our agent. We try to run this thing again. We can say, okay, the victim agent was able to just ignore the attack behavior and then just try to win the game. And then we do another round of demonstration is that we try to retrain an attack agent against our victim, say what can happen, whether the attack agent still establishes that weird behavior or not, whether our victim or our agent is still vulnerable to that weird behavior or not. Turns out actually it's not, right? So the attack agent cannot find that some shortcuts in the victim agent's policy. The only thing it do is just try to block it. And then the defense agent or victim agent is just strong and then can bypass it. Right, that's basically our talk. I will just, for the sake of time, skip conclusion and just leave flow to the questions.